some variables that are required in the metal cutting, like shear angle. What is shear angle? If you know the rake angle. And what is R? R is the cutting ratio. Then we have seen the different velocities. So there are three. VC is chip velocity, cutting velocity is V, Vs is the shear plane velocity of the chip along the shear plane. So those things, and we have seen the relation between them. Okay. Then after that, we discussed the merchant theory. It depends on orthogonal cutting. There are assumptions. So mainly assumptions are related to orthogonal cutting, and the material is assumed to have a fixed TS, tau S. Okay, that is shear strength that is fixed. That is the main assumption. Others are related to orthogonal cutting only. So with those assumptions, and of course we have seen the different forces acting on the cutting tool or the chip or the workpiece. Okay, based on the component you are considering, it may be either tool or the workpiece or the chip. So in our analysis, we have finally considered the forces acting on the tool. Okay, forces acting on the cutting tool. You can consider the chip also. In some textbooks, they will consider the forces acting on the chip or the workpiece. Okay, all are same only, because ultimately total forces acting are cancelling out and you are getting a steady state process. And it is very important to understand the this merchant theory. So there are different forces acting, mainly four different forces are acting on the tool. We will consider tool for the time being. So what are the forces acting on the cutting tool directly? Or at least a chip and a tool interface. What are the forces acting? A chip tool interface. Please respond. What are the forces acting at the chip and a rake interface or tool interface? See, I don't know whether you are following the classes or not. Okay, the force acting at the chip tool interface is friction force, and of course opposite to, not opposite, perpendicular to that will be the normal force related to the friction. So that is the force acting at the chip and the tool interface. And of course at the chip and the workpiece interface, or at the shear plane, we have the shear force acting along the shear plane and a normal force to the shear force. So those are the four forces. Because we cannot measure those forces directly, we will measure the cutting forces coming on the workpiece using a dynamometer. You'll keep the dynamometer just below the workpiece, and on top of that you will fix the workpiece and you will do the machining process, and you will measure the horizontal forces and vertical forces coming onto that workpiece. So because we can measure only FC and FT, that is cutting force and thrust force, so now we have to convert the forces like friction force and normal force into FC and FT individually, and similarly we will convert Fs also in terms of FCFT and N normal force, that is Fn normal force to the shear plane, will also be converted to Fc and Ft because those are the known forces. And finally we will write Fc. Okay, in terms of Fs we know, and Fs can be further divided to As into tau s, and As is the shear plane area and tau s is the shear force, and As will be now written as a W, okay, T by sine phi, and you will find out the shear angle for the minimum force requirement. Okay, that is what that was the analysis done by the merchant, and 2 phi plus beta minus gamma is equal to 90 degree. That is the final result. So that theory is applicable for only rigid plastics, synthetic plastics rather. For metals, it is not completely applicable. Okay, now let us continue from there. Yeah, I am revising all this just to make sure that there is continuity, and you will revise the concepts once. Use this. Not getting the record option here. What happened? Not getting the record option for some reason. I don't know. Anybody could see the record option for this meeting? I'm not getting the. Let us start. Anyhow, still I am not getting this record option. I could not figure out the reason for that. So I'll continue anyhow without recording this session. So I'll just show this for once. So construction of a merchant circle diagram, okay, is important. You generally, in some of the numerical problems, you will be given one or two, at least some information, partial information will be given. You have to find out the remaining information. Like you will be given the FC and FT, and you have to find out what is Fs, what is Fn, what is F, what is N, okay, what is beta, etc. So the first thing you will do is, if FC and FT are given, you will draw them like this. So you will convert FC into some scale. and ft also. So based on that, you will construct one, okay, you will draw one horizontal line based on the quantity of fc, then one vertical line, okay, related to the quantity of ft. Then you will okay, join those ends and you will form this, okay, triangle, right angle triangle. Then gamma is known to you, rectangle. So from the tool geometry, so with that you can draw a line, and of course before that you construct a circle with the capital R as diameter. So then you draw one line at angle gamma. So wherever that line is meeting this circle, that will up to that point it is equal to f. Then you can join the end of f with the resultant force. So then you will get n and you can get beta also. And once you know phi value, you take phi and draw one line with that from this corner, then you will get fs, then you can get fn from there. Okay, this is how you can get different forces acting during cutting process. And of course we have seen the analytical relations also. Okay, how will you write fs in terms of fc and ft? If you know phi value or gamma value, you can find out those forces analytically also. Of course, for merchant theory, we have seen this. Okay, tau s is written like that. Tau s is a function of Fi. Okay, there are some assumptions. So all these things we have seen. Okay, just I am going through all this. So here we have understood that merchant theory is good for synthetic plastics. It is not suitable for metals. It will give approximate results. It will not give correct results. So there is a scientist called Bridgman. He has now proposed that tau s is equal to tau SO plus K into sigma S. So where K is a material property, sigma S is the normal force acting on the shear plane. Now according to modified merchant theory, okay, so this is FC. We have got from merchant theory, FC in terms of Fs, FC is equal to Fs cos beta minus gamma by cos phi plus beta minus gamma. So the same equation we have used earlier in the merchant theory. Now what is the modification? Tau s is changing. Tau s is equal to tau s4 plus k into sigma s. Now it can be further written as tau s0 plus k into what is sigma s? Sigma s is the normal force acting on the shear plane. So what is the force acting? Fn. Fn is the force acting normally on the shear plane. What is the area? As. So Fn by As is nothing but sigma s. Now what is Fn? From the merchant circle, Fn is equal to R sine phi plus beta minus gamma. Okay. So what is Fc? Fc is equal to R cos beta minus gamma. That is also there. Now from this relation, okay, from these two, you can write, okay, you can divide these two. Fn by Fc is equal to sine phi plus beta minus gamma by cos beta minus gamma. So Fs will go on the right hand side. So finally, Fn is equal to Fc sine phi plus beta minus gamma by cos beta minus gamma. So the thing that you have done here is you have just taken tau s as this, and now sigma s is converted to Fn by Fs. Now you have converted Fn also into Fc. Okay, because finally we know Fc, Ft and beta, gamma, phi, these values only we will come to know. So based on that, we have to find out. Now you take this Fn and substitute here. Okay, in tau s. Now tau s will become like this. Tau SO plus K into, okay, so this FC sine, okay, this is nothing but the Fn value, and you have the sine phi divided by TOW is related to the AS. Okay, so that is tau s. Now we have already proved that FC is this. Just in the previous slide, first equation was this only. Now you substitute tau s here. Okay. Now FC will become like this. Substitute tau s. So what is tau s? This value as it is you are taking. So you are putting it here. That is tau s. Okay. And you put the remaining things as it is. K times of this. Okay. All this stuff coming here. Okay. So further, okay, simplify this. You'll get tau s into TW, okay, TOW by sine phi and cos beta minus gamma divided by cos phi plus beta minus gamma. And if you take it into this, it will be KFC, because sine phi plus beta minus gamma is here, cos phi plus beta minus gamma here. So it will become tan phi plus beta minus gamma, cos beta minus gamma will be cancelled out. Okay. So we'll get it in this expression. Is it okay? Remaining things will also get cancelled out. This is the equation. FC will become this. Now you multiply, you take the denominator, this, okay, this one into other side. So it will be, okay, finally, you just rearrange the equation and you will get FC times of 1 minus K tan phi plus beta minus gamma is equal to tau SO TOW by sine phi into cos beta minus gamma. This is the equation. So finally, FC is equal to this. So our aim is to get FC, okay, in terms of the known values. What are the known values? Gamma, beta, phi, TO, W, tau SO, all these are known. So somehow you have to convert FC into that format. We cannot directly say FC is equal to FS times of something. That is correct. But FS we should know. We don't know. So that's why we are converting everything into known values. Now there are some constants here. Tau SO is constant, TO is constant, W is constant, beta, gamma are constants. Gamma is anyhow constant, beta is assumed to be constant, okay, because we are assuming a steady state process. And only variable is phi here. So you take the denominator now, okay. So if the derivative of your denominator, we are optimizing this FC, okay, we have to minimize that. So if the denominator, its derivative is 0, then we can get the optimum value for FC. So you take this and derive it. Okay, here it is sin A cos B minus K times of sin A sin B. Okay, so you derive those two equations with respect to phi, partial derivation. So cos phi cos phi plus beta minus gamma, sine has become gamma. Sorry, initially cos, because sine phi has become cos and remaining thing same. Then this is sine has become, it was cos earlier, this was there, cos phi plus beta minus gamma. If you derive that, it will become minus sine. So minus has come here. So sine phi this. Derivation anyhow, all of you are very well aware. So then minus of this quantity. Okay. Now finally, because cos A cos B minus sin A sin B is cos A plus B. So cos 2 phi plus beta minus gamma. On the other hand, it is cos A sin B plus sin A cos B. So what is this? Cos, sin A plus B. Okay, 2 phi plus beta minus gamma. So this is the equation. Now if you take them to one side, they will become cot 2 phi plus beta minus gamma is equal to k. So finally, you can write 2 phi plus beta minus gamma is equal to cot inverse k. So k is a constant. So cot inverse k is a constant. So 2 phi plus beta minus gamma is a constant. Earlier also in merchant theory we got the same, but there it was fixed pi by 2. 2 phi plus beta minus gamma was pi by 2. So here it is a cot inverse k. Now what is, you can say, did I go back? So this is cot inverse k. Just some extra slide has come. So this cot inverse k is called, okay, machining constant. Cot inverse k is called machining constant, 2 phi plus beta minus gamma. So only thing is now tau s is also dependent on sigma s, normal shear, normal stress acting. Okay, so from that you will get this. So this is called a modified merchant's theory. Okay, so remaining things are same. So now it is applicable to metals also, not all metals, particularly ductile type. Now there is another version of this cutting force analysis that was proposed by Lee and Schaefer. Okay. So earlier in merchant theory, we have assumed that there is a plane called shear plane. Okay, along that, the chip is getting separated. Okay, from the workpiece, and shear force is maximum along that, or shear force is acting along the shear plane only. Okay, for the convenience, we have made such kind of assumption. Now Lee and Schaefer have told that, okay, they have proposed that, okay, shear force is not acting only along the shear plane. Okay, or the material is not getting, material is getting plastically deformed along the shear plane. That was the assumption in merchant theory. Now the material is getting plastically deformed over a volume or a small zone, according to Lee and Schaefer. It is not along a single plane. So what they have proposed is, they have used the slip line theory. We are not going to discuss that slip line theory concept here. So from the slip line theory, what are the final conclusions? Okay, we'll talk about those conclusions only. So here, this is the plane along which the shear force is maximum. That is okay, but this is not the only plane along which shear force, okay, shear force is acting. So this plane is making angle phi. That is fine. Now, from this end point, okay, AC plane, you take 45-degree line to this shear plane. Okay, so the volume contained by this triangle ABC, AB is along the rake surface. So within this volume, the material is subjected to plastic deformation. So that is the assumption made by the Lee and Schaefer. And the chip is trying to move perpendicular to the shear plane. So along this. So primary deformation for the chip is along the shear plane. And there is one more deformation or the, okay, deformation also you can say, slip lines will be observed in this fashion also. But this is secondary, not primary. Okay, within the chip, you will find this kind of, okay, separation of the chip, okay, along this plane, but it is not a major, it is difficult to visualize that. So that is there. Now we know alpha is here, rake angle is alpha here. Okay, so from textbook to textbook notations are changing. This is not gamma now. And if I draw a vertical line here, this is alpha now. So here you see these equations. Angle CAB, this is equal to 45 degrees plus beta. Okay, so 45 degrees, this angle is equal to 45 degrees plus beta. How it has become 45 degrees plus beta? This angle. So here you see angle between, okay, N and F is beta, we all know that. Okay, that is beta. And this is alpha outside. So this is 45 and this is some other angle, total angle here. Just a second. This is becoming now 45 minus beta. This is 45 plus beta is here. So finally beta is here. Carefully observe. Beta is here along this slip line and R, resultant force. So this will become now, this is 45. Just just a second somehow. This is 5. How it is becoming 45 minus beta? Just so if anybody knows this, so they can also talk. Just I have seen this, but forgot somehow. Angle CAB is 45 plus beta. CAB 45 Beta is the angle between F and N. Okay, maybe I'll come back to this later. So if you know this, so that is fine. Somebody, I'll just give. I'll explain this little bit later, maybe in the next class. Okay, again. But for the time being, you understand that angle CAB is equal to 45 degrees plus beta. Somehow I'm not getting that logic only. So I'll re-explain this later. CAB is equal to 45 degrees plus beta. If that is there, then okay, phi plus CAB is equal to 90 degrees plus alpha. Now what is phi is here, CAB is this, okay, that is equal to 90 degrees plus alpha. So it is very clear now. So this is 90 and this is alpha. So phi plus CAB is equal to 90 plus alpha. That is very clear. Okay. Now phi is equal to 45 degrees minus beta minus alpha. Because CAB is 45 degrees plus beta, you substitute it here. So from that, phi is equal to 45 degrees minus beta minus alpha. So phi plus beta minus alpha is equal to 45 degrees. So this is the theory they have developed. Phi plus beta minus alpha is 45 degrees. Alpha is here rake angle. So from this, if beta is equal to 45 degrees and alpha equal to 0, then phi should also be equal to 0 to satisfy this equation. So high friction and a low rake angle. Why we are saying high friction? Beta 45. So tan 45 is 1. So that is the upper limit for the friction coefficient. So high friction and low rake angle, or in fact it is 0. Okay. That leads to formation of built up edge. And this phi is becoming 0. 0 means okay, in fact shear plane itself is coinciding with the cutting force direction. Okay, it is just a 90 degree like this. Okay, chip has to just turn in it. So friction will be very, very high. And you will have built up edge in that case. And if you have some negative rake angle also. So like, for example, if beta is 35 degree, so less than 1 is the friction coefficient. Alpha, let us say, is minus 10 degree. Now again phi is equal to 0. So that means the tool is like this. Okay, friction angle is also varying. Again you are getting phi as 0. Phi may not be 0 in that case. Okay, it will be something different, maybe like this. Okay, so it is not practical. It is not okay. Practically we are not getting that, but theoretically from this theory we are getting that. So that is the drawback here. So it is not applicable. It is not completely applicable for the metal cutting process. So let us do one. Acha, okay, these things. Have I stopped presenting? No. Let us quickly see this. Now all of you must remember this merchant theory, different forces acting on, okay, how to get the minimum cutting force, all that. And finally, and of course, the Lee-Schaffer theory also, where we are considering tau s is tau so plus k into sigma s. And here, that is modified merchant theory. So here in Lee-Schaffer, it is phi plus beta minus gamma is equal to 45 degree. That's it. Okay. Now power. Okay, once we know force, we can find out the power. Now cutting power is PC into FC into V. So PC is equal to cutting power. PC is equal to cutting force into cutting velocity. Now if you convert that into horsepower, you can divide by 60 into 746. Now power is dissipated mainly in the shear zone and on the rake face. So those two locations only most of the power is consumed. So power required for shearing action, if you consider that, PS is Fs into Vs. Fs is shear force, Vs is the chip movement along the shear plane direction. Now power to overcome friction, that is Pf is equal to F into Vc. Okay, F is friction force, Vc is the chip velocity. Now actual motor power required will depend on the machine efficiency definitely. So you will not have 100% efficiency. So you can write actual power required, motor power required is equal to PC divided by this zeta, because we need more power. So we have to divide this into 100. Okay, if you are suppose you are using some 100 horsepower, but only 90% of that is used in the metal cutting process. Okay, so remaining some waste will be there into 100.
So wonderful.
Yeah.
Before one, why are we? I mean, like, while converting into horsepower, why are we dividing again with 60, sir?
See this FC and V, they are in newtons. Okay.
Yes, sir.
Meter per minute. Understand?
Yeah. Yes, sir. Yes, sir. Okay.
So
for converting that into seconds. Okay, I got it, sir.
Unit conversion only.
Yes, yes, got it. Understood.
Okay. Now material removal rate is okay. Up to here, you have to understand this is the P is equal to PC by that efficiency, maybe zeta, eta, whatever, into 100. Now material removal rate, what is material removal rate? Volume of material removed per unit time. So volume removed by time. So what is volume removed? Length into width into uncut chip thickness. That is the volume removed from the workpiece, from the slab. Now time to move a distance L for the cutting tool is the length covered is L, cutting velocity is V. So by time is this length by velocity. Now you can rewrite this as MR is equal to L into W by T O by L by V. So if you cancel out L, it will be V into W into TO. So that is MRR, material removal rate. Okay, those are the units in general. Mm cube minute, meter cube per, sorry, mm cube per minute is the unit for material removal rate. Now unit horsepower for removing unit amount of material. Okay, so what is the power required? or otherwise for removing 1 mm cube material, what is the power required? Okay, so HPC by MRR. Now specific energy. Okay, this is not the specific energy we discuss in okay, thermal engineering or thermodynamics. Here this is specific cutting energy. Okay, so for unit amount of material removal, what is the energy required? So that is defined as, for cutting process, UT is the specific energy. Specific cutting energy is the better word. So that is PC by MRR. Okay, energy required for removing the unit material. So this is energy again. Okay, now FC into V divided by V into W into TO. Okay, because this is MRR, PC is FC into V, MRR is V into W into TO. So finally we have FC by W into TO is the specific cutting energy. For shearing to take place, what is the minimum specific energy? PS by MRR. So this is Fs into Vs by V into W into TO. To overcome the friction, what is the specific energy? PF by MRR. That is F into Vc by V into W into TO. So overall, UT, cutting energy required, specific cutting energy required, is equal to US plus UF. Because for cutting to take place, you have to overcome the friction and the shearing action. Okay, both are taking place during the cutting. So total cutting energy, okay, is the summation of these two. And of course, some okay, minor losses may be there, but we assume that those are negligible. So ultimately, UT is equal to US plus UF, shearing friction. Okay, if you take the energy consumed in the shearing process and the friction process between the chip and the rake surface, the total energy consumed is equal to the cutting energy. Now, as UF increases, that means friction energy is requirement is increasing. Shear angle decreases. Okay, as the friction force is increasing, shear angle decreases. That we know from our merchant theory also, 2phi plus beta minus gamma is equal to 90 degree. And hence, US also goes up directly. So from this relation, okay. So friction is increasing. So shear is decreasing. So once the shear angle is decreasing, US is increasing. Now, friction plays an important role in metal cutting. Okay, we all know that, because there is, during machining process there should be some friction, otherwise there will not be any machining at all. Understand? This cutting tool will just slip off from that region. The cutting and thrust forces are derived as follows. Tau-S is shear strength, we all know that. Fs is Tau-S into As, very well known. Fc is equal to this from merchant theory. Ft is equal to this. Okay, all these are known quantities only. So other forces can be derived from the equations of previous slides. They were nothing but the equations we have got from the merchant theory. Fc is equal to this. This is okay. This has come from the merchant theory. Ft is equal to this. This again has come from the merchant theory. So we have expressed both of them in terms of Fs, where Fs is equal to Tau-S into As. All these have come from the merchant circle. Now some violations, because we have made many assumptions and we have used the merchant theory. We have derived the merchant theory from that. So this okay, theory may not be applicable at all the times, because there will be some violations during machining process. So some of the violations are geometry and form violations. You have assumed that there is a zero rake angle. We have not explicitly stated that, but we have assumed that there is a zero rake angle, okay, in orthogonal cutting. And you have also assumed that there is a sharp tool tip. Okay, you have not considered any nose radius. So this is one violation. Understand? You have not considered those. Is the thing. Now shear takes place over a volume, not a line or plane. We are talking about merchant theory. So shearing is taking place over a volume, not along a single plane. So that violation is there. Okay, in practice, so it is volume, but you have assumed a plane. Now cutting is never a purely continuous process. Okay, chip will not move at the constant velocity throughout. Why? There may be some cracks in the chips and material may not be homogeneous. Due to that property, the chip sometimes will slow down and it will move at a higher velocity at some other place like that. Now size effect. Larger stresses are required to produce deformation when the chip thickness is small. Size effect is not at all considered. It is not considered many times actually. So if you want to remove a large volume of material, the amount of force required to remove unit volume is small. If you want to remove less volume, so the amount of energy required for unit material removal is high. I hope you understood this point. So let us say this is one volume that you want to remove. This is another volume. So you consider this has some 4 units of area. So this will have many units, maybe some 16, 20 units, same. So this unit area here and this unit area is same. But this is a larger volume, this is small one. So if you want to remove this material with less force per unit volume, you can remove this quantity when the size is high, large size. The size is small, for this same unit volume removal, you have to exert more force. Okay, I think in practice also, if you see, if you want to remove one sticker from some wall, okay, or some pad, let us say, you have to exert more force to remove that. Understand? If you have some thick sticker, okay, it is very easy to remove that. If you have very thin slice, you have to exert higher force. That is size effect. So that is not considered here. Okay. Now built-up edge, some workpieces materials, okay, they will form built-up edge during the process, but we have not considered the built-up edge process formation. If built-up edge is there, so forces will vary. Okay. Now this is one figure you have to understand. So this is the workpiece material. Different forces acting during the cutting process. You have already studied them, but try to understand the directions of different forces. Now Px is the horizontal force that is acting during cutting process. Pf is the force acting on the cutting edge in this direction. Pz is acting in the downward direction. Understand? Now what is PZ? We have represented that with thrust force Ft. PZ is nothing but Ft. Okay. So Px and Py we have not shown in our derivations earlier. So the resultants of Px and Pf, resultant of that is Pxy is nothing but Fc, cutting force. So if you cut this along this orthogonal plane and view this process, so this is Pxy, that is cutting force. This is Pz, that is thrust force. Okay, Ft, Fc. Okay, this is another notation given in another textbook. Pxy is equal to Fc and this is Ft. Okay. Now, what is this phi? This phi, what is this phi? Principal cutting edge angle. Okay, not the shear angle. So this is phi. If this is phi, this is 90 minus phi. So if this is 95 minus 90, because this is also 90 degree. This is 90 minus phi. Obviously, this is phi. So from this, we can write Px is Pxy sin phi, because this is phi. Similarly, Py is Pxy cos phi. And the resultant force, final resultant force acting on the tool is this. So that is nothing but Pz and Pxy, resultant of that. Okay. So that is there. Now Pxy is anyhow resultant of Px plus Py. Now what is Pz? Tangential component taken in the direction of Zm axis, that is nothing but Ft. Pxy is axial component taken in the direction of longitudinal feed. Py is radial or transverse component taken along the Ym direction. Okay. So sometimes you will be given Px, Py. You have to find out the Pxy, that is cutting force, and thrust force will be separately given. Okay. I think, yeah, with this we'll stop our lecture for today, and we'll solve some problems in the next class. Unfortunately, we could not record. I'll try to figure out. Yeah, if you have any doubts, any clarifications required in this, we can discuss. Only one small angle portion I could not explain. I'll definitely explain that in the next class. Any other doubt if you have? Okay, fine. So all of you go through this, okay, merchant theory. Not only that, from the starting, from tool geometry, all this is very, very important. Okay, generally in any interview, core jobs particularly, so these concepts will be asked. Okay, if they are asking some questions from manufacturing, means they will definitely ask a few questions from metal cutting. It is very sure. Tool signature, how tool is designated. Okay, what are the angles? What is the significance of those angles? Clearance angle, rake angle, etc. Merchant theory, there will be many questions. Why you are doing the force analysis? Why you are going for merchant analysis? Okay. And what is the relation? What is this cutting ratio? Everything related to merchant theory. They will be very thoroughly asked in any interview related to core jobs. And not only that, if you are attempting any IES, okay, definitely there will be one question on merchant theory. In GATE also there will be many questions coming from this metal cutting. Manufacturing means metal cutting is the most important. Other parts are important, but okay, main focus will be on this. So all of you thoroughly go through these okay concepts. Okay, that's all for today. I'm closing the session. Have a nice day.
Thank you, sir.
Thank you, sir.